We will now move on to the various ways in which GANs have been improvised over the last few years, talk a little bit about disentangling of VAEs, and then move on to applications of GANs to images and videos. Let's start with a few improvements over vanilla GANs. The first method that we'll talk about is known as StackGAN. This was published in ICCV of 2017, and the goal of this work was to generate reasonably good resolution 256 cross 256 photorealistic images that are conditioned on text descriptions. So here is a high-level flow. The entire GAN model is conditioned on a text description. It could be a caption, for instance, and standard NLP methods such as word-to-vec, glove, bird, so on and so forth are used to get an embedding of this text description, which is provided as input to the GAN. With that input, in the first stage, the GAN generates 64 cross 64 images with perhaps a few high-level details or low-frequency details. These images are then provided as input to the next stage of the StackGAN, which generates 256 cross 256 reasonably high detail photorealistic images. And both these stages are conditioned on the same text input. Let's see the entire architecture now. So you have the text description, which is given as input to the entire StackGAN. In this particular example, the text description reads, "This bird is grey with white on its chest and has a very short beak." So you obtain an embedding of this text, as I just mentioned, using say word-to-vec or glove or bird or any other embedding of your choice. And this embedding is then added to the standard Gaussian noise that's given to a GAN. So you can see that you get a mean and standard deviation from this embedding. And this mean and standard deviation is used to obtain a sample. And that sample is concatenated with a sample from the standard normal. So that becomes the entire input to the generator, to the first stage generator. So the first stage generator then goes through an upsampling generator module, which generates a 64 cross 64 image that you see here. Now, the generated image and a set of real images in a given mini batch are provided to the discriminator, which downsamples these images. And before the final step of classifying this input as real or fake, you also include the embedding phi t again here. So you see here that there's an arrow that comes all the way and gets combined to this output of the downsampling module. And the job of this discriminator now is to classify this tuple of generated image, whose representation we are considering, which is this blue block here, and the text embedding together to be real or fake. This is the first stage. The second stage, the results of the first stage is given as input along with the embedding of the text again. Both of these then go through the second generator stage. So you can see here that the image goes through a downsampling, then the text embedding is then concatenated to that downsampled representation. This then goes through a set of residual blocks, which is then upsampled to get the final output 256 cross 256 image, which is what you see here. Now that goes now to the second discriminator, where you give the generated 256 cross 256 image and one of the real 256 cross 256 images. Once again, the output of the downsample representation is concatenated with the text embedding, and the discriminator has to classify each such tuple as real or fake. Now let's understand how the discriminator can look at the tuple and classify real or fake. So in this case, there are three kinds of scores the discriminator has to obtain, has to provide. So the first one is when the real image is provided with the correct text. Obviously, the discriminator would want the score of such an input to be 1 because both are correct. There's a real image and the corresponding correct text. There is also another setting where you have a real image and an incorrect text. In this case, the discriminator should ideally give a low score. Similarly, you have a fake image with a correct text, which the discriminator should give a low score, but the generator should try to increase this particular score. These are denoted as S sub R, S sub W and S sub F. Now let's try to understand how the optimization actually works. So the StackGAN alternately maximizes the discriminator loss and minimizes the generator loss, similar to what we saw with the GAN. In this case, the discriminator, as we just saw, would try to maximize the log likelihood of the first score and minimize the log likelihood of the second and third scores, which is what is given by the second and third terms here. We just saw that when we understood these scores. Similarly, the generator tries to maximize log of 1 minus SF because that's the job of the generator. It also tries to minimize the KL divergence between the output of the mu's and sigmas that you see in the initial layer at the end of the text embedding with the standard normal distribution. Here are some results that are obtained from StackGAN. What you see on the top row is a baseline method called GAN int CLS that was published in 2016, and the bottom row shows the results of the StackGAN. So you can see here in the first column, the caption says, "This flower has petals that are white and has pink shading." You can see here that the quality obtained by the StackGAN is far more photorealistic than of earlier methods, and this holds for all these images that you see at the bottom row. Another popular method that came in 2018 is known as the progressive GAN. The progressive GAN is designed for generating high resolution images up to 1024 cross 1024. And the key idea is in the name of the method itself, is the method progressively grows the generator and the discriminator. We'll soon try to decipher what this means. This work was published in ICLR of 2018. It also had a few other design decisions, such as using a standard deviation in a given mini batch, a concept of an equalized learning rate, and a pixel-wise feature vector normalization in the generator, which we will also see soon. So the progressive GAN has an overall idea as what is shown in this image on the left here. So the generator first produces a 4x4 image, which is what is shown in the leftmost part of this image here. So you have the latent vector that comes from a standard normal, a very simple network which generates a 4x4 image, and this is provided to a discriminator D along with a real sample to be able to judge whether it's real or fake. This then increases to 8x8 in the next iterations of training. You can see here that compared to the image generated in the 4x4 setting, the 8x8 setting is still blurry, but has some more details when compared to the 4x4 setting. You can also notice here that there are some layers added in the generator as well as the discriminator when the next higher resolution is generated. And this is repeated over and over again until we get a final generation of 1024 cross 1024 image. The key idea that this allows is for stable training of GANs for generating high resolution images. Whenever the progressive GAN goes from generating a certain resolution to the next higher resolution, as I just mentioned, there are new layers introduced. How are these layers introduced? This procedure is very similar to ResNets. So you can see that in this subfigure B here in the image. You see now that while you had an initial resolution 16 cross 16, when you step up to 32 cross 32, the nearest neighbor interpolated version of the 16 cross 16 layers output, when you interpolate, you get a 32 cross 32 output that is added to the 32 cross 32 layer through a skip connection. How is that added? You can see an alpha and 1 minus alpha here. So the new output layer is, the final output is given by alpha into the new output layer plus 1 minus alpha into the projected layer. By projected layer, we mean the output of the nearest neighbor interpolation. This allows progressive GAN to fade in new layers in an organic manner to be able to generate better images. As I mentioned, progressive GAN also introduces a few other design decisions. One such contribution is known as mini batch standard deviation. In this step, the standard deviation for each feature in each spatial location over a mini batch is computed and averaged. So you can imagine now that when the generator generates a particular feature map, you take every spatial location, which is every pixel, you compute its average across the entire mini batch. You will get a certain standard deviation for that value across the mini batch that is concatenated to all spatial locations at a later layer of a discriminator. Why do you think this is done? Think about it. It will be your homework for this lecture. Another contribution that progressive GAN brings to the table is known as equalized learning rate. In this case, the weights in each layer of the generator network are normalized by a constant C, which is specified per layer. So this constant C is a per layer normalization constant. Why is this done? This allows us to vary C in every layer and thus help keep the weights at a similar scale during training. So why is this called equalized learning rate? Because the value of the weight effectively affects the gradient and hence the learning rate. While methods such as ADAM, ADAGRAD, so on and so forth adapt the learning rate, they may end up having low values when the weights themselves are very low or very high. Normalizing by a constant allows these weights to be of a similar scale during training across all of the layers. This allows better learning. Another contribution that progressive GAN makes is a pixel-wise feature vector normalization in the generator, where for each convolutional layer in the generator, the normalization is defined as AXY, which is the xyth pixel in the 8th feature map, divided by 1 by n, where n is the number of feature maps, summation j going from 0 to n minus 1, that's across the n feature maps, axy superscript j whole square plus epsilon. The denominator here considers the pixel value at the same location across all of the feature maps and normalizes the value at the 8th feature map with this denominator. The epsilon here is for numerical stability to avoid a divide by 0 error, and the output is denoted as bxy, which is the normalized value. With these contributions, progressive GAN reports impressive results. Their results are compared with earlier work such as Mao et al. And Gulrajan et al. And one can see that with the progressive GAN approach, the result is fairly photorealistic and high resolution with more details when compared to earlier methods. A third, more recent improvement of GAN is known as StyleGAN, published in CVPR of 2019. This looks at progressive GAN, which is also known as ProGAN, which generates high quality images but does not give the capability to control specific features in the generation. For example, it's difficult to use a progressive GAN and say that you'd like to take an image and add a certain color or change a particular attribute in the image. StyleGAN's objective is to be able to control the generation of an image using a particular predefined style. How does this do it? It automatically learns unsupervised separation of high-level attributes. Could be examples could be pose and identity for face images, stochastic variation such as hair, which could have a lot of randomness, and scale-specific control of attributes. The intuition for StyleGAN is that a coarse resolution in an image, if we consider face images, could affect attributes such as pose, a general hairstyle, face shape, etc. If you go to the next level of resolution, anywhere between 162 and 322, this resolution throws in finer attributes such as facial features, more specific hairstyle, eyes being open, closed, so on and so forth. And at the highest resolution, a fine resolution anywhere between 642 and 10242, affects the color scheme both for eye, hair and skin, as well as introduces micro features on the face. StyleGAN tries to address and introduce some style specific components at each of these resolutions to attain its desired effect. How does it do this? Given an input random vector, the same as in the vanilla GAN, StyleGAN first normalizes this vector and then sends this through 8 fully connected layers without changing the dimension of the input and obtains a 512 cross 1 vector. Remember, the input latent was also 512 cross 1, so these 8 fully connected layers do not change the dimension of the input. And this transformed vector, which we call W, is given as input to the generator or the synthesis network. Now let's see how this vector W affects different resolutions in the generation. This is achieved by introducing a matrix A which learns an affine transformation at different resolutions. So you can see here that the synthesis network or the generator in StyleGAN has an upsampling module and then has something called as adaptive instance normalization, which we will see in a minute, which is followed by a convolutional layer and then another adaptive instance normalization layer, and then this is then repeated over multiple blocks. Let's take a look at one of these combinations of convolutional and adaptive instance normalization layer. So if you have a convolutional layer here, as what you see on the top here, a specific channel of the feature maps in that convolutional layer is normalized by its mean and variance to get an adaptive instance normalization. Before that's concluded, the weight vector W, which was obtained here, which is given as input to each of these blocks, is transformed by an affine map which gives us a set of values YSI and YBI, which is used to change the scale and bias of the output of the convolutional layer. This is where the adaptive normalization comes into play. So you can see here that this now becomes xi minus mu of xi, which is normalization with respect to mean and variance. So this quantity here in the inside corresponds to subtraction by mean and division by variance. It is multiplied then by YSI, which is a scaling value obtained as an output of the affine transformation A, and then biased by YBI, which is also the output of the affine transformation. Note that these values YSI and YBI could be different in different blocks of the synthesis network, and each such transformation thus defines the visual expression of features in that level, and that allows the input latent to have a different influence at different resolutions of generation. Another method, a recent one, which was published in CVPR of 2019 again, is known as SPADE. We'll see it expansion soon. And the key idea of SPADE is that previous methods directly feed the semantic layout as input to the network. You have a certain image and the entire semantic layout is known with the pixel configuration of the image. And in SPADE, which is given by spatially adaptive normalization, the input layout for modulating activations in normalization layers happens through this spatially adaptive learned transformation. Let's see how this happens. In the standard batch normalization layer, you could look at the output as going through an affine transformation. You scale up the value and you add a constant, which is an affine transformation, which is the standard batch norm operation, where you have a value, you multiply it by gamma and add a beta, which together defines an affine transformation. However, in SPADE, what is done is a semantic segmentation map is given as input, and this semantic segmentation map goes through a convolutional layer, and the convolutional layer outputs a gamma and a beta, which is used to normalize the previous layer of the generator. So as you can see here, unlike blindly normalizing the output feature map in a specific layer, in this case the normalization is done in a spatially adaptive manner, where the gamma and beta come from the spatial relationships in this semantic segmentation map. What is the semantic segmentation map? Recall that a semantic segmentation map has a pixel-wise association of a class label. So you can see here in this sample, you have a tree, you have a sky, you have a mountain, you have grass, and you have a road perhaps. That is used to define the gamma and beta for normalization. A random latent vector can also be used to manipulate the style of generated images, but the semantic segmentation map gives a way of normalizing using spatial content at each pixel. So you can notice here that the normalization now is defined at each pixel. these gammas and betas are defined at the pixel-wise level, which is what is denoted by the cross here and plus here, which are done element-wise, which can allow each pixel to be normalized in a different way based on the semantic segmentation mask. Here are some interesting results. So you can see here that the semantic segmentation output is given as the input to SPADE. So these are masks of semantic segmentation, pixel-wise class labeling, and this is the actual ground truth image corresponding to these semantic segmentation masks. You can see here, while the third and fourth columns correspond to other methods, SPADE gives a fairly photorealistic output close to the ground truth. And what you see here is the architecture of the generator in SPADE, which is similar to many other GAN architectures, but for the input of the semantic segmentation mask coming in at each layer. Finally, the last method we'll discuss in this lecture is a very popularly used one these days, known as BigGAN, which was published in ICLR of 2019. The focus of BigGAN was to scale up GANs for better high-resolution generation. It was designed for class conditional image generation, which means the input is both a noise vector, similar to a vanilla GAN, and some class information. It could be a one-hot vector, for instance, which together are given to the GAN to generate an image corresponding to that class. BigGAN also introduces a few different design decisions, as we will see in the next few slides. An important design decision in BigGAN is to use the idea of a self-attention GAN or a StackGAN, which is actually an earlier work that was introduced in late 2018 and published in ICML of 2019, which introduces the idea of self-attention. We already saw self-attention in transformers a week ago. It's the same idea here, where you have a set of convolutional maps in as the output of a particular layer in the generator. This goes through multiple 1x1 convolutions. Certain 1x1 convolutions undergo transformations and are transposed to obtain an attention map. These three branches are very similar to the query, key, and value of the transformer architecture. You could consider them to be similar at least. So two of those branches generate an attention map which is used to focus on a specific part of the convolutional map to then generate that component of the image in the next layer. Why is this required? Self-attention GANs were introduced because often GANs, while they generated crisp images, they would miss out finer details. For example, in a dog's image, they may generate the fur on the dog but miss out the legs of a dog. So the idea of using self-attention is to focus on specific parts of the image and generate every local detail more properly. In BigGAN, along with self-attention GAN, the loss that is used is hinge loss. This hinge loss is similar to the hinge loss that's used in support vector machines, which is given by max of 0, 1 minus ty, where t is the target output and y is the predicted output. This is because BigGAN is class conditional, so you also want the output image to belong to a particular class, which is then used at the discriminator stage, because the discriminator now no more only says real or fake, but can give a class label whose loss in this case is given by hinge loss. In addition, BigGAN also introduces class conditional latents in a slightly different way. Instead of a class conditional latent, which could be a one hot vector, instead of giving that directly to the input of the generator, the class conditional latent is given as a separate input at multiple stages of generation, where it's concatenated with certain input and then given to each of these residual blocks. What is done inside each of these residual blocks? The concatenated class label vector passes through a linear transformation, two different linear transformations in fact, which is given to the two batch norm layers inside each of these residual blocks. BigGAN also had other design decisions which helped its performance. One such was spectral normalization, where the weight matrix in each layer was normalized to ensure that its spectral norm was maintained, and it also satisfied the Lipschitz constraint sigma of W is equal to 1. You can see this paper called Spectral Normalization for GANs, ICLR 2018 for more details. The broad idea of such a step is similar to batch normalization, to constrain the weights with certain properties that ensure that learning can be better and faster. In this case, we try to constrain the highest singular value of the weight matrix. A second idea is orthogonal weight initialization, which is a well-known weight initialization method where each layer's weights are initialized to ensure that W transpose W is equal to I, or the weight matrix is orthogonal. It also introduced skip Z connections, which we already saw, where the input latent Z is connected to specific layers deep in the network. It also introduces another method known as orthogonal regularization, which encourages the weights to be orthogonal in each iteration of training. How is this done? Using a regularizer R subscript by beta, where beta is a coefficient, where the regularizer tries to ensure that the Frobenius norm between W transpose W and identity is minimized. So this would be a way to ensure that W transpose W is close to identity and hence the matrix is orthogonal. Why? Why would we want orthogonal regularization? Think about it. This is another homework for you for this lecture. Other hacks that were employed in BigGAN were the discriminator model was updated twice before updating the generator model in each iteration. The model weights were finally averaged across a few training iterations using a moving average approach, which was used finally. This was also done in progressive GAN. BigGAN also observed that using very large batch sizes such as 256, 512, 1024 and 2048, when we say batch sizes, we mean mini batch sizes while performing mini batch SGD. In fact, they observed best performance with the highest mini batch size of 2048. They also doubled the model parameters or the number of channels in each layer, and they employed a trick known as the truncation trick, where while the generator initially receives a latent vector from a Gaussian during training time, at test time you sample a latent from a Gaussian, and if that value is less than a threshold, you discard it and sample another value. So this is called a truncated Gaussian. You could now imagine that this truncated Gaussian is something like this, where you're ensuring that something sampled below a threshold is not considered as input to the GAN. So that way all inputs to the GAN come from this part of the PDF, which the main idea being is that you would not get anomalous generations using these latent vectors, but you get generations that belong to the core part of the PDF of that Gaussian. Your homework for this lecture is go through this excellent survey of GANs that was recently released, chapter 20 of the deep learning book, and here are the code links for most of the GANs discussed in this lecture if you'd like to see them and try them out. The questions that we left behind are: why is mini batch standard deviation used in progressive GAN? And why is orthogonal regularization used in BigGAN? Think about it and we'll discuss the next time.